Get started. So last time we talked about physics-informed neural nets. Um, the idea of neural net that we've been building is basically some parametric representation of mathematical relationship. So and then we're interested in modeling the position x of that Spring-Mans-Stemper system as a function of time t. So that for any given time t, we can predict the position of the system, right? Predicted by the neural network over here. The idea of physics-informed neural net was nothing more than a regression, right? So we basically wanted to regress the neural network prediction x with respect to the ground truth x hat, so that the difference between the x hat and the predicted x gets minimized. And our goal is to find the optimal parameter configuration to minimize that prediction error was the one thing. But then obviously in the real world scenario, we do not have the luxury for the most of the time to afford a large number of x hat to train our model, right? So in case of computer vision and medical imaging applications, there were millions of images available. So we have millions of x hats, right? And then we could train our model on that large data set. But in our case, patient or experimental results, we cannot that much of that many x hats, which is why we're introducing some secondary loss term called the physics-informed loss. The idea of physics-informed loss is excuse me. The idea of physics-informed loss is that since we do know the governing equation of the system, which for the harmonic oscillator case is mx double dot plus cx dot plus kx equals to 0, right? We know that mathematical relationship. We're going to use that relationship to define additional loss term, so that using that loss term, we can further fine tune the theta, right? So for the information that are not covered by the data loss terms. Data loss terms are some scattered points in the data space, right? And for the areas where we do not have those observations, we're going to be relying on the physics-informed loss term was kind of the idea, right? Now, for many of the governing equations that governs physics, so not necessarily just the Spring-Mans-Stemper system, but also many other physical systems will involve some kind of a derivative, right? Which is why they're called differential equations, right? At first place. So you're going to be, you're going to need to take the derivatives of some neural network model quantity x, okay, with respect to time in this case. Also, for the cases of PDE, you will also need to take the derivative of x with respect to some, some other quantities like position vectors and so on and so forth. And then, for that kind of derivatives, we saw last time the automatic differentiation, and then the pi implementation of automatic differentiation, which is called the autograd. So, operationally speaking, what you could do is to take the automatic derivatives and then compute the derivative terms, and then construct the physics-informed loss term, and then you could train your model. Last thing as a recap, we also saw that the physics-informed loss terms were evaluated at the locations called the co-location points. Those co-location points are, usually an arbitrary sampled set of points in the physical domain. So again, in our case over here for the spring mass damper system, our physical domain is only the time domain t, right? But for other little more sophisticated cases, like the ones that we're going to see today, the physics may define, maybe defined not only over time, but also with respect to some space or position vector r. So what you ought to do is to sample some random points in that physical domain, right? And then on those randomly sampled points, you evaluate the physics-informed loss terms. And remember that for the evaluation of the physics-informed loss, you do not need the ground truth, okay? For data loss, you needed to, evaluate the x hat. You needed to have the x hat to define the loss term itself, and you needed a ground truth. But in case of physics-informed loss, there's no ground truth. Okay, you just need to take the derivative of the neural network, construct the equation, flow all the collocation points through that, neural network, evaluate the PD residual or the residual of the governing equation, and that is all you need. So what that means is, without having to worry about the cost of sampling the ground truth, right? You can have as many collocation points as you want, and then you can have to use that to refine the training of the physics-informed neural network. Okay. Yes. Questions. That is a great question. So for the sampling of the collocation point, the default setting is to just go with a uniform random sampling. Okay, so you just uniformly sample across the physical domain, and that is by default what you would need. But later we're gonna see that for some complicated physics, you may need to actually sample the collocation point more strategically, so that whenever, for example, nonlinearity happens, whenever there's some, sharp change in dynamics, or some interesting things happening in the boundaries, and so on and so forth, you may want to sample your collocation more, much denser in those locations. Whereas when the dynamics is kind of smooth and nothing interesting happens, then you can reduce the density of the sampling. Yeah, yeah. If you similar to that, we can allocate collocation points, much denser near the area where the physics is, expected to be, much more sophisticated. Whereas in the smooth areas, you can kind of sample less. So there are adaptive sampling strategies, and we're going to be, talking about that soon later in today's lecture. Other questions? Yes. Hmm? Ah, that's a great question. So if your governing equation is in the integral form and there's no way to make it a differential form, then I think you're going to have an issue. Although I cannot think of a specific example where that might be the case. So most of the time, you should be able to, convert your equation into, something that looks like that. And in fact, we're going to introduce more generic form of governing differential equations. And I think 99% of the time, you will have that kind of representation. So there's no concern there. But for whatever reason, if your governing equation happens to have integrals and things like that, then it might be actually difficult to define the physics and form laws because numerically integral is something that is very difficult to compute. Um, the computation of the integral itself will require some additional numerical methods like Runge-Kutta fourth order or other solvers. So in that case, I don't know, defining physics and form laws is going to be, a practical thing to do. That's a great question. All right, maybe one more question and then we can move to the yes. Oh, the weight term applied to the data loss and the oh, that's a great question. So you probably noticed in my sample code that there was some number multiplied to physics and form laws. The bottom line is if you too strong, too big of a physics and form loss, then your model will not converge at all. So for most of the differential equations, there's a trivial solution, which is called not doing anything. So like in this case, for example, the PDE residual can be made 0 if x equals to 0. So if you don't do anything to your system, the position stays the same, no velocity, no acceleration. So all three terms are 0. Then, the PDE residual is 0. So that's a trivial solution. And when the training begins, if the physics and form loss term is too dominant compared to the data loss term, then numerically speaking, it'll try to converge to that trivial solution of not doing anything. So your neural network will simply just spit out zeros all the time and then not converge anywhere. So as a matter of fact, in the harmonic oscillator example, last time we saw that, we could fit this, vibration curve. But if you increase the weight term for the physics and form laws, what's going to happen is the neural network will be a flat line for the entire time interval. Because not doing anything, right, staying in the same position is the best way to, the easiest way to, at a data loss term. And then once the system, the neural network sort of converge, then you want the physics and form loss term to start to kick in. Okay. So in theory, you gotta have some small, weight applied to the physics and form loss term compared to the data loss term. But then how small is small, right? You want to have an adequate value. If it is too small, then basically there's nothing, no difference between physics and form neural network and just a regular neural network, right? versus, like I said, if the weight value for the physics informed loss is too high, then it's not going to converge anywhere. And that is, in fact, one of the downsides of physics informed neural network. It is very difficult to train. It is very, very difficult to train, and there are a lot of hyperparameters like that. So it's going to require lots of trial and error. Okay, and if it requires lots of trial and error, it sort of defeats the purpose. I mean, the purpose of using neural network and machine learning approach is to make it a rapid approximation, as opposed to like spending a lot of time in solving the the physics system in a rigorous manner. But if the training takes that long and lots of trial and error, the practicality of PIN becomes a little questionable. So we're gonna actually take a look at that later today more in detail. All right, lots of great questions. So what I would like to do today is to generalize this a little bit, and then make it applicable to sorry about that. Yes. So no matter what kind of physics problem that you consider, at the end of the day, it will boil down to a homogeneous PDE, where we have the partial derivative of the physical quantity. So this is the quantity that's evolving over time. And that rate of evolution is defined by some differential operator n, okay, that takes the physical quantity u and spit out some other function. So an operator is kind of function of functions. An operator takes a function as an input and then will spit out another function as an output. So d dt, the first derivative, you can consider it as that as an operator. d dt, what it does is to take a function as an input, and then we'll spit out the first derivative, which is another function, right, as an output. So we assume that there is some relationship given in this manner. We also, in terms of the terminology, we also consider that the variable x is a position vector in the physical domain omega. So omega is your physical domain. If it is a fluid dynamics problem, most of the time, the shape of omega is kind of a rectangular box, right? Or if you're considering, finite element analysis of some structural, component, then omega is basically the 3D volume defined by a CAD model, right? And of course, that omega is embedded in RD. So that's the D-dimensional Euclidean space. So a lot of times, we consider 3D or 2D, right? So D is either 2 or 3. We'll see a one-dimensional heat equation soon. So in that case, D equals to 1. And then also the time variable t is another very important variable, because obviously we're talking about a time evolution of a physical quantity. And then we consider that the time t is defined in the interval 0 and t, which is a subset inside of a real line. So, given that kind of a PDE, we call u of t solution function. Now our goal is to find u, okay, satisfies this relation, right? Is what we would like to do. From now on, we're going to be using subscript annotation to, the sake of brevity. So use of t is typically in the PD literature denotes partial u partial t, the time derivative of the, the solution function u as a shorthand. Like I mentioned, n is a nonlinear operator parameterized by some, physical parameter lambda. So lambda, for example, can be things like the stiffness matrix of, your solid system, or it could be the Reynolds number defining the fluid flow. Any physical parameter that governs the physics is represented as lambda, and then operator n is factorized by those physical quantities, so that the rate of change is defined by those physical quantities as well. And then finally, omega, like I said, is the physical domain whose boundary is denoted as partial omega. So here's a very simple example of a physics problem that will follow this form, right? So linear convection diffusion equation is an equation that describes, two things, a diffusion where, quantities like temperature will start from, one kind of, concentrated location, and then it will start to diffuse. And then, the heat is going to be delivered to the surroundings, right? Convection is, convection is a, phenomena where instead of heat sort of diffuse and, getting delivered to the surrounding, the material itself kind of move around. So when you, for example, boil water, right, the water will kind of, start to flow, right? And because of that movement of the water particles, the heat will, move to, from one location to the other location. So that is, what's called a convection. So the convection diffusion equation over here, equation describing those two phenomena acting together. So again, when you boil, then the heat will diffuse, right? But in the meantime, the material itself will also move, right? And in that way, the convection phenomena and the diffusion phenomena happens together. And mathematically speaking, the convection diffusion equation looks like this. So we have the partial derivative of u, okay? So u is the physical quantity that is either diffused or convected. So temperature is an excellent example, right? So partial u partial t, the rate of change of that physical quantity, is defined as we have the first order derivative term, which is the convection term. And then we have the second order derivative, which is the diffusion term. Okay. So C over here is the convection coefficient. And then the nu over there is the diffusion coefficient. And those coefficients will determine how well, for example, a material, move from one location to the other location. So that's the, convection coefficient. And then nu is, certain physical can be, passed along from, one location to its neighborhood. So that's what's determined by nu. So in this setup, okay, this whole thing over here So except for the time derivative, this whole thing over here is basically our nonlinear operator, okay? And that nonlinear operator is, parameterized by C and nu in our case, right? And that, nonlinear operator does is to take a function u and then spit out the derivative, du dx minus d square u dx square. Generic nonlinear PD. So in this example, we have a linear PD, but you can see that, any generic nonlinear cases can be covered by this representation. Oh, actually, one thing I forgot to mention is that there are some PDEs where we have the right-hand side comprised of some function, which is called the control input. So robotics, for example, the right-hand side typically, indicate the control input coming from the motors or some, other, actuators. So for pin, we do not consider those right-hand side, okay? Although there are a lot of papers in the literature that handles the control inputs, okay, inside of the pin. For the control input, in case you have a control input, it's a little bit more complicated because the control input is a separate thing and than the physical quantity u, right? The control input is the thing that is independent, and that independent input will, change the response of the system, right? So in that case, you're going to need to model the control input separately than the neural network representing u, right? And then you gotta, hook them up together. But because of the complexity, we do not consider that in the scope of this class. But hopefully, after learning this, generic problem setup, you should be able to, read the relevant literature and then, see what's going on. All right, so Raisi et al., those are the people who first proposed the physics-informed neural network back in 2018. And in their paper, their actually pin paper is comprised of two parts. So there are two separate papers, part 1 and part 2. And in each of those parts, they propose a slightly different use cases of pin. So the first part, they talk about the data-driven solution of PDEs. So given a partial differential equation, how can we solve those partial differential equations using a neural network is the part 1 of this paper. Whereas the part 2 is what they call the data-driven discovery. So it's a slightly different nuance. In case of the data-driven discovery, you do not have the actual parameters. So last time we saw, the zeta and the omega 0, right? Those were the physical parameters in our harmonic oscillator system. And then we started from the assumption that, those parameters were given. We knew those parameters. But in many, real world scenarios, there may be situations where you do not know those parameters, but want to determine them from some sort of an experiment. So let's say instead of knowing the zeta and omega, let's say you only have some, video recording of a spring mass damper system, and then you track the position of the of the mass, and then from there you want to reconstruct the damping coefficient and the angular frequency, right? So in that case, we're talking about a data-driven discovery of PDEs. So I'll walk you through, those different applications, maybe with a slightly more sophisticated physics problem. You still do not have anything. So you want to figure out the model of, describing the system, but in the meantime, find the optimal zeta and omega, as you go along with the optimization. Yes. Yeah. Yes and no. We're finding the operator in the sense that we're finding the parameter lambda. We're not actually finding the operator. So what I mean by that is, let's say you have some totally unknown physical phenomena. In that case, you don't even know what the nonlinear operators look like, right? So in that case, the neural network will not be able to discover physics for you. So the term discovery is, again, in my opinion, it's a little bit of a misnomer, because we're not really discovering the PDE, out of blue. It's more like you already know that overall the physics will follow certain equation. You just want to figure out the coefficients of that PDE. Yeah, yeah, just finding lambda. Yeah. So in fact, we're gonna see some, other problems, not today, but tomorrow and then Wednesday, where we have absolutely no idea what's going on about the physics. You just have some, measurements from experiment, and then from there you want to, truly discover what's going on. So for those kind of problems, PIN is not the solution that, the method that you're looking for, but there are other methods that could be useful for those. So, okay. All right. So data-driven solutions. Um, I know there's a lot of math, so, but bear with me. So for data-driven solutions, we led U theta, subscript theta, to be a neural network with the parameters theta. So theta is a collection of weights and biases in your neural network. And with that U theta, what we would like to do is to approximate the solution function ut of u of t and x using that U theta. Now, the assumption here is that we're given two things. One is data. So the data must be given at some time t and the physical location x, right? And for those, t and x, we expect that there's, the corresponding physical value u, right? So in terms of the notation, we use the superscript I with the parenthesis to denote ith point in your data set. So, again, either from an experiment or some sort of a numerical simulation, we assume that we have this, tuple of t, x, and u. And then that is what for the data loss. And then, another thing that must be given to be able to driven solution, problem equation, including the, actually not some, but the entire set of parameters must given so that you can define the physics informed loss term, right? So those two are the most crucial things to define the loss term for the training of PIN. And then from there, our objective is to train the neural network U theta, or figure out the optimal set of parameters theta that minimize the following objectives. One is the data loss, and then the other is the physics loss. So the data loss is the usual mean square error, and then the physics loss is, like we saw, the residual of the partial differential equation. Hmm? Hmm. Yes, yes. So if you have both, physical experiment data and numerical data, then you probably want to treat them differently. For the numerical data, since the numerical data is deterministic, I think practically what people do is to add some noise to inject some uncertainties. Otherwise, the model training can be biased to the deterministic set of data, right? So yeah, they must be treated differently, like you said. Does that answer your question, or okay? Any other questions? Now, a little more on the physics informed loss, or the PD residual term. The collocation points are the points, like I said, defined as the pair of the location in time and the location in space. And like I said earlier, you do not need ground truth value with physical quantity. So note that there's no U involved in the definition of the physics informed loss. So somebody asked, what is the distribution of those collocation points? So usually we consider the uniform distribution in the space-time. So what that means is, whatever the range of, the time interval is, and whatever the, your physical domain look like, your best bet is to, just uniformly sample points in that space time and location points accordingly. There are some fancier, like I said earlier, methods to sample the collocation points. So instead of the uniform distribution U, you can sample points from some arbitrary probability distribution P. Okay? So similar to what you do in traditional numerical simulation, you can adaptively sample T and X. So the probability P can be a heuristic where you evaluate, you increase the probability of sampling as you is, I don't know, violent. So determined by the the magnitude of the gradient, for example. If the magnitude of the gradient is high, that means there's something, violent, something interesting is going on, some dynamic stuff is going on. So in that case, you can increase the probability of sampling. So there are a lot of different sampling methods, and we're going to see some of them in later slides. But essentially, the uniform distribution is kind of the default setting if you don't know where to begin with. So are you concerned about like moving boundary problems? So for the initial condition, I mean, you don't have to worry too much about it because um, the user pin, so for the initial value problems, initial condition is given already. So, you can sample. Actually, initial conditions are usually, fed in as data loss. So if you're given an initial condition, then you already have, some ground truth, right, at time t equals to 0. And those ground truth data points can serve as the data loss. For the boundary, it's the same thing. It's a uniform distribution over the Cartesian product of the time interval and the boundary. So what that means is we're considering if you have some complex, geometry to define the boundary, we're considering that, during the uniform sampling. So again, if you have a CAD model, for example, then you want to sample points inside of that CAD model if you're talking about some solid mechanical problem. Or if it is some fluid phenomena with certain boundary condition, again, you got to consider the geometry when you do the sampling. So this very definition is generic enough to consider to include all kind of boundary conditions and a little more sophisticated to implement, but theoretically speaking, there's nothing that prevents you from including those boundaries. Does that answer your question? Mm, yeah, yeah. So here I brought the you know, a slightly more sophisticated example, which is the heat equation, slightly more sophisticated compared to the harmonic oscillator. We're still in the very, simple case. Um, heat equation is a, very simple PDE that describes the diffusion of heat through a given region. So the equation looks like this, where lambda is essentially the diffusion coefficient. And then what the heat equation says is that the rate of change in temperature is basically the same as the second order derivative or the curvature of the temperature distribution. So when there's a bump, for example, of the temperature distribution, that bump will produce some, large second derivative, right? And because of that bump, the heat will flow in the direction of, removing that bump. And then, after a certain period of time, the temperature will reach the equilibrium where, it is the same everywhere, right? So that's what this equation, stands for. And our goal is to find the solution function u given the diffusion coefficient lambda, as well as the initial condition. So initial distribution of temperature is already given. So it's an initial value problem. So this is something that we're going to see after the break with that, PyTorch session, within that PyTorch session. But, here we consider that the initial condition is given as a sine function. So to make it simple, we have a rod, okay, of the length 1 meter. And then over that rod, we have the temperature distribution that looks like this. The temperature is normalized onto some, scale ranging between 0 and 1, so that we don't get to handle like crazy large numbers. Now, the reason why I brought the heat equation as an example is because heat equation is one of the very few PDEs where the analytic solutions are known. For most of the PDEs, there are no known solutions, so there's no ground truth that we can compare against. But in case of the heat equation, the ground truth of the heat equation is analytically given. So in case of this initial, condition, this is essentially the analytical solution for this initial value problem. As a matter of fact, this condition, you can, describe the solution function u at arbitrary time t. Okay, so no matter how crazy your initial condition is, the solution is going to be this, the exponential part, times that crazy function describing your initial condition. So that's one of the really nice property of heat equation. And later on, so this is kind of a preview of tomorrow's lecture, actually. Somebody noticed that many of the initial value problems are in the form of some operator times the initial condition. Okay, so instead of learning the u directly, what about we learn self is another kind of way of thinking about physics learning problems, right? So you could learn the u directly, right? You could fit your neural network directly onto the solution function u, but you could also learn called the solution operator. So that is, by the way, what's called a neural operator approach, which is going to be the topic for tomorrow. And then, even more clever way is the solution. The PDEs will always look like and instead of learning this entire thing with exponential term included, what the term over here, right, inside of the exponential function, is another idea that you could employ, which is called a physics-aware recurrent convolution, or PARC. Okay, so that's actually what my group has been working on. So, just as a preview in connection to the other problems, in today's lecture and then the last Friday, we've been talking about the way of approximating u directly using neural network. But then we'll see that, that kind of methodology can, create a lot of problem because the U itself can be, highly nonlinear. You know what I mean? Like the harmonic oscillator, it's a linear ODE. But despite the fact that it's a linear ODE, the final trajectory, right? The curve itself is very nonlinear, right? So if you are to, like, if you consider a neural network as a curve fitting, right? You're fitting the curve on this crazy trajectory versus the operator itself. Again, in case of a harmonic oscillator, it's exponential of some matrix times t. Okay. So it's a linear matrix at the operator level. Okay. So if you train your model on the operator instead, instead of the solution function itself, you can simplify the learning problem from a very highly nonlinear curve fitting problem to, much more linear line fitting problem. And obviously line fitting is much, simpler than curve fitting. So that's kind of, the evolution of thoughts that we're going to be seeing, throughout this week. So if that doesn't make sense, don't worry, we'll get there. But for now, we'll just move on. So in terms of the, how do we solve this heat equation using PIN? So in terms of the design of the neural network, what we're going to do is to have T and X, the input to the neural network, okay? Because we are talking about 1D heat diffusion, right? We have only a one tangential rod. We only need one variable for the position vector and then one variable for time t, right? So those two are the inputs to the neural network. And then what happens is we have a bunch of fully connected layers, or the linear layers, right? And then at the end, we spit out, the temperature U, okay, as the output. So in terms of the neural network design, now we have, repeated the same thing multiple times. So at this point, you should be able to parse code over here. So we have a bunch of linear layers, and then the way it works is, you take the linear transform, and then followed by the exponential ReLU, and then we repeat that a few times, and finally spit out the final output. Now, in terms of the physics-informed laws, this is something that we learned last time, torch.autograd.grad, right? So in this way, you can take the derivative of any arbitrary, any sophisticated function, as long as you have a computational graph available. So what happens is we have two parts. The first part is where we define the data loss. The second part is where we define the physics-informed laws. The data loss, super simple. For given input, you infer the model, right? Make the model predict something. And those predicted temperature values are then compared directly against the ground truth outputs. And that's what defines the data loss. So data loss, super simple. The physics-informed laws might be a little more sophisticated, but as long as you understand how torch.autograd.grad works, then, again, this is not, terribly difficult. So for the physics-informed laws, first of all, we start with some collocation points. And given those collocation points, we have predictions here. So we have a slightly different, variable name to distinguish them, but, we have the, predictions basically. And then using the autograd gradient, we take the derivative of this prediction with respect to the collocation points, and then we have the derivative. Now notice that since we have n, we have two derivatives, okay? So the first part of the derivative is dt, the second part of the derivative is dx. And in our case, for the heat, we only need a dx part. And the dx part is mute. Oh yeah, there we go. So here's a setting. Here's more graphical, view of what I just walked you through. We're gonna actually see this in PyTorch after the break, but just to give you an idea, we have the initial condition, right, given already, and that is what defines the data loss. So the red dots over here is the data loss. And then we're going to assume that we do not have any other ground truth data loss, okay, to solve this heat equation. So we're using a neural network as kind of a numerical solver for this differential equation. Okay, we just start from the initial condition and that's it. Now for collocation points, we're going to set a mesh grid of 12 by 12 grid points. Again, here I just uniformly sample, but I could, for example, have more collocation points earlier in time because I know that in the diffusion equation, the dynamics is more interesting at the beginning. And then once you converge, once the temperature diffuses, then the dynamics is not going to be as interesting as before. So I could, increase the density of the sampling with smaller time t, but here, for the simplicity's sake, we're just using a uniform sample. Well, actually, I should have explained how to read this plot. So for those of you who are not, in the mechanical, major, this plot may not be, as familiar. So we have the evolution of time, okay? And then here's the position x. So the rod is in this direction. And then the temperature distribution. So imagine a cross section of this surface, along, this direction, right? That cross section is what represents the temperature distribution at time t along the direction of the rod. Okay, so we have some, physical rod, and then initially the temperature distribution was like that, following the sine function, and then it diffuses and then kind of flats out, as you can see, as the time evolves. And here's the animation showing the training process of PIN for that particular setup. So see, initially, it's a flat plane. So the blue grid is the PIN. And initially, PIN initially pin is like a flat surface. So that is the trivial solution. At the very beginning, without the data loss terms, um, you know, the easiest way of, reducing the physics informed loss is by saying, oh, there's nothing happens in the temperature. It's constant everywhere. That's the easiest, trivial solution. So we start from there. And then because of the data loss, initially, the network fits the red dots predominantly. And then as we repeat more and more iteration, you can see that the blue surface gets kind of deformed to fit the actual physical process. Any questions so far? It's funny. It's funny to see that the CS side of the classroom, last week was like, very engaged and following very well, whereas the engineering side of the classroom was struggling last week. This week we have the opposite. The engineering side over there is doing great, and they're nodding their head. Yeah, that makes sense. And then the CS started to be like, "What the heck is that?" We assume that the initial condition is given. Yeah, yeah. Laws. And we do. Sorry, I'll get to you. We do have collocation points at time t equals to 0, so that might answer your question as well. Yeah. So. Right. Um, you could, for example, run direct numerical simulation for a few time steps and then produce some data points and then use pin to fit the rest. But I don't know, that doesn't sound very realistic to me, right? I mean, if you're in a simulation lab, usually running the simulation takes a lot of time, and the whole point of doing pin is to avoid that time-consuming process of running simulations, right? So, yeah, so that's why, but it doesn't mean that you cannot have the data loss somewhere else than time t equals to 0. You can very well have whatever data points you want to have. Yes. Yeah. Yeah. That is a very big possibility of that happening. Yes, that's true. Yeah. And You're right. So in fact, just among us, it took me a while to get this animation. It was very difficult to fine tune the parameters and things like that. So, um, and despite that, you can see that the pin is not perfectly accurate. And then I tried, more than 20,000, steps of iterations. I ran it all the way up to 100,000, 200,000, 300,000. It still looks like that, even for such a simple problem like the heat diffusion. So um, that's kind of an inherent, I guess, inherent downside of PIN, which is, the physics informed loss is the only thing that drives um, the training procedure. And then, you may end up in a erroneous solution like that. Is one thing I want to say. The other thing I want to say is, um, this is something that we're going to be talking about later in this class. But the data loss and the physics informed loss doesn't necessarily are aligned together. So reducing the data loss doesn't necessarily mean reducing the physics informed loss, and vice versa. Reducing the physics informed loss doesn't necessarily mean reducing the data loss. So during training, what happens is the data loss term and the physics informed loss term produce the gradients that are in the opposite direction. So the data loss term suggests that the model should be changed in this direction, whereas the physics informed loss suggests that the model should be updated in the other direction. And those directions can conflict. And as a result of that, sometimes actually, it kind of diverges, where initially it sort of, start to converge that, to look like this, but then all of a sudden it pick up in some weird gradient, and then, the solution kind of goes crazy. Or it stales like this and then never able to, be perfectly accurate. So those are kind of the limitations of PIN that are inherent to the design of the method. But if you have more data, then yes, I think the performance of the network is going to be much better. But you will still have that issue of conflicting physics informed loss and the data loss. So, yes. Mm. Yes, for sure. Yeah. So we're already, criticizing the limitations of PIN, and that was actually going to be the topic of the later slides. But you're absolutely right, because the dilemma here is, if you want to, make it more accurate, you probably want to add more collocation points. But then adding more collocation points means more computational time. So, that is kind of the trade-off that you have to fight. Yes, yes, yes. So if you have a boundary, um, some interesting geometric boundary, then oftentimes, I mean, the collocation points needs to be assigned near those boundaries, and then you're going to need a lot because, like in case of Navier-Stokes, for example, the fluid behavior will change dramatically near those boundaries. So when you have like a sharp, protrusion or, anything like that, you're going to need to allocate a lot of collocation points over there. But then computationally becomes super expensive, and it becomes like, oh, I would rather just solve a, Navier-Stokes equation directly, as opposed to training this thing, because it takes more time to train pin and to solve the numerical solver. So any other questions? All right. Speaking of Navier-Stokes, here's another example. Unfortunately for this one, we're not going to do it in the class because, like I just said, this takes forever. So I frankly don't see the reason why one would use pin as opposed to, you know, direct numerical solvers, especially if you have high Reynolds numbers and, you know, things like that. I personally don't find the practical need of using pin. But I mean, still, this is kind of an interesting idea. And then, you know, pins obviously have evolved. So the original, you know, formulation of Raisi et al. May not be useful for solving complex problems like Navier-Stokes, but there are other variants of pin that might actually be, you know, practical in this case. But again, for the purpose of this class, we're going to stick to the original, you know, formulation of Raisi et al. So Navier-Stokes, in case you don't know, is an equation that looks kind of like this. It's an equation that describes a flow of water or any fluid object. So if you're a mechanical engineer, this is probably something that will ruin your third year and fourth year in undergraduate. And then if you, you know, are unfortunate enough to take the career in aerodynamics or fluid dynamics, this is something that you will struggle with for your entire life. But here we have a two-dimensional case, and it's incompressible, so it's a relatively simpler form of Navier-Stokes, which happens to look like this. Okay, it may look a little, you know, intimidating at the beginning. It's really nothing more than the combination of the first derivatives and second derivatives of u and v. So u and v here are the velocity of the fluid in the x component and the y component velocity. And then the x velocity and y velocity follow this this relationship where the rate of change in the x velocity, that's the u sub t, right? The rate of change of the x velocity is somehow governed by the velocity gradient, right? So the x velocity, the gradient of the x velocity in the horizontal direction, the gradient of the x velocity in the vertical direction, and then the dot product between the gradient and the, you know, current velocity. So that's what's called the advection term. And then we have the pressure field. So x component of the pressure field obviously affect the change in the fluid velocity in the x direction. And then we have the diffusion term over here. So u xx is the second derivative of x velocity along the x direction 2 times, right? And then u yy is the derivative of the x velocity in the y direction 2 times. And that is what defines this whole thing. And then mu is what's called the viscosity. So yeah, so in case you are from you know, engineering background, this might be a good opportunity to kind of brush up what you've already learned. If this is the first time seeing this equation, don't worry. Just get the feel that, you know, the time derivative is described in terms of the first order and the second order derivatives. Something complicated going on, but this is what governs the flow of water, flow of air, you know, all kind of cool stuff. Oh, and then one thing I forgot to mention at the bottom is the conservation of mass. So here we have the x derivative of the x velocity plus y derivative of the y velocity, and that needs to be 0. And that is just a mathematical way of saying that you know, this amount of water flowing into a control volume and the amount of water flowing out must be the same. So that, you know, means that the um, divergence of the water flow needs to be zero so that, um, you know, no water is created or disappear. So again, training this takes a lot of time, so I didn't even bother to, you know, create a PyTorch example for that. But the original authors, they have published their code, which by the way is written in TensorFlow. But if you're, you know, since you already know PyTorch, TensorFlow syntax is not terribly different. So if you're curious, I encourage you to, you know, check out the, you know, their implementation. But here um, we have vortex shedding. So somewhere over here is a cylindrical cross section, and then the water is flowing around that cylindrical cross section. So imagine, like, you know, you're driving a car, you stick your arm outside of the car, and your arm is roughly a cylinder, and then the air will, you know, flow around that cylinder and create all kind of, you know, weird kind of a demonstration of predicting the vortex shedding, you know, behind the cylinder using using pin. Um, Obviously, you know, for the Navier-Stokes equation. Oh, sorry, one more thing. In this example, now we're talking about the discovery problem. Okay. So not only the velocity field, the pressure field are the unknowns. So the you know, the coefficients, the fluid viscosity and the fluid density, those are the you know, those are set as the parameter. And you know, this is nothing more than just, you know, like in terms of the PyTorch syntax, nothing more than just setting, you know, requires grad equals to true for rho and mu, and then you update, you know, rho and mu together as you train the neural network. We're going to see the, you know, the actual implementation, you know, something equivalent to this in the Python. So you know, they look pretty accurate, right? So this was kind of the demonstration that's, you know, in their paper. Now, one thing I want to mention though here, since some of you mentioned, I mean, ask questions about the boundary condition and things like that. Um, they actually did a sneaky, thing of not presenting the cylinder, So they actually set a control volume behind the cylinder and did not really, present the result around the cylinder. And later on, people discovered that pins are not very good at respecting the boundary conditions. So actual predicted pressure, you can see that, the water sort of, penetrate into the cylinder, and the cylinder is now, filled with some flow of air or flow of water. And then they kind of, only presented this, this section of the vortex shedding phenomena. And then because of that, it kind of, sort of promoted other, directions of research, which is to, enforce the strict boundary conditions inside of pins. But that work is still kind of ongoing. So that is actually one of the sneaky things that we also discovered, among my students and I. We were kind of messing around with pin, and then we've been, facing with issues where, water keep, just into the, no matter how location points we set, near the boundary, it eventually goes in. And that kind of continuity, if it is something that the neural network will, struggle of modeling, because it's a curve fitting, it's a surface fitting in this case. And then if you have continuous boundary, you have a curve shape that is, kind of discontinuous, right? So fitting, yeah. So, pin being a regression model, have a discontinuity that, it'll struggle. So, so that's something that I wanted to, to mention here. Um, well, I do think they have the bias in the model already, but despite that, somehow the actual pressure values are a little off. And then the authors did not, particularly give any answers to, why the color bars is different. So I don't know. All right. So the summary so far is, PIN at the end of the day is a regression model with some soft penalty defined by the PDE residuals. And then, we could essentially do two things: either, solve the, PDE where the solution is unknown, or on top of solving the PDE, you could also discover the physics parameters. So those are the two use cases of PIN. Pros, obviously, implementation of PIN is super simple. It doesn't involve any, complicated implementation. It's basically a regression model. The only thing that's added is the, PyTorch autograd.grad. And then as long as you can compute the derivatives and, implement your own differential equation, that's all you need to do, right? And the implementation is super simple. So it gained a lot of popularities. And then, from the perspective of the applied physics community, you have two things, right? Fancy, deep learning, that's the big buzzword in the academic community. And then it sounds like the deep neural network is respecting some physics, or based on some physics principle because of the namesake, right? Physics informed neural network. So it gained a lot of popularities in the CFD community, in the, mechanical engineering community, civil engineering, like wherever, the discipline is, wherever you need the physical equation, and want to somehow model that using, data-driven method, it gained a lot of popularity. And then, like many other technologies, when you have a shiny hammer, everything's starting to look like a nail, and then you want to hit the nail with that shiny hammer. So PIN I think until now, like even until now, is considered to be a shiny hammer for, to a lot of people. And then you get to see a lot of publications that involve PIN, and then people solve some kind of an equation using PIN. But like I mentioned, there are a lot of challenges and also research opportunities. So the original formulation of Raisi et al. Especially is not particularly useful in many reasons. And then there are a lot of research going on to improve PIN, make things better. So here is one particular paper by Krishna Pryan et al. In 2021, where they kind of investigated PIN more depth, and then they kind of came up with a set of benchmark test problems to reveal pros and cons of PIN. So one of the benchmark problems that they came up with is the 1D advection equation. So 1D advection equation, the partial derivative of u is described as a linear function of the spatial derivative, first order derivative. And 1D advection equation describe a phenomena where the matter a matter moves in one direction. There's no diffusion, there's no creation of the matter, anything like that. It's just just a pure transportation. So you have the initial condition described as sine x, and then according to this equation, what happens is the sine wave just moves. Okay. And then in their setup, we assume the periodic boundary condition so that at x equals to 0 and x equals to 2 pi, the values are the same. So if you were to train PIN on this problem, you would need the PD residual, the physics informed loss, right? The initial conditions serve as the data loss terms. So for a given xi, we know that at t equals to 0, it has to satisfy sine x. And then we also have the boundary condition, and the boundary condition is another kind of data loss term. So we have data loss term coming from the initial condition and the boundary condition, and then we have the physics informed loss term. And guess what? So let's look at the exact solution first. So this is the exact solution. This is the x direction, and then this is the y direction. Sorry, this is the temperature direction. Time direction. What am I talking? So we have the x direction, the time direction. What happens is the sine wave, okay, initially on this x direction is evolving over time, okay? And then, like I said, the 1D advection equation describes the translation of the sine wave. So if you, in your mind, if you, take the cross section of this chart, right, in the vertical direction, you will kind of you will kind of see that the sine function is moving, from here to here. So, this is the peak of the sine function at the beginning, right? And that peak, as you can see, is moving in this way as the time goes. So that's what is, is governed by that equation over here. So if the neural network was perfectly accurate, then it should be able to produce this result, okay? Notice that the beta, the advection coefficient, or simply speaking, the speed of translation is relatively high. So beta equals to 30 is the situation we have. So, when beta is large, obviously the stripe pattern is gonna, you know, be steeper, right? When beta is small, then, you know, the translation will happen more gradually like this. Now, with that in mind, look at the pin solution for beta equals to 30. Okay, you will see that the initial, you know, sine wave segment gets advected properly, but then in terms of the boundary, you know, the periodic boundary condition, it's not really respecting the boundary condition. And in fact, it fails to predict anything, you know, after time t equals to, I guess, 0.2. 0.2 is roughly when the initial sine wave kind of, you know, makes its, you know, full translation, right? And then after that, it doesn't really, you know, predict anything. So, you know, from this, we kind of see that pins are actually not very good at, you know, preserving the boundary condition. And I just mentioned a few slides ago that, you know, the Navier-Stokes example, they somehow sneakily, you know, did not report the cylindrical cross section in the paper. If you look at the error rate as a function of beta, you can see that with the growth of beta, you know, the error kind of sort of jump up quite dramatically. And again, we have the low velocity regime on the left. We have the higher, relatively higher velocity regime on the right. And then the error kind of goes up quite dramatically. And, you know, notice that this is a log scale, log scale. So the jump of error is actually more dramatic than what you see from this chart. Are we doing on time? Okay, perfect. Here's some more examples. So when beta equals to 10, like I said earlier, it's a relatively slow speed. And in that case, it, you know, preserved the prior, you know, periodic boundary condition. And then it was able to, you know, make the prediction accurately. Here's the error plotted over that, you know, xt space. And then we're in the order of 0.02. So relatively small error, about 2%, roughly speaking. So everything looks good. But then the moment beta goes up, you can see that as the beta goes up, you know, the stripe pattern becomes, you know, much more frequent and then, you know, steeper. And then you can see that the model just gives up, you know, preserving the periodic boundary condition, and then we get to see a lot of errors. Any questions so far? Now, the fact that pin struggles with boundary conditions and, you know, advection in general doesn't mean that there's no hope, right? So if you still want to use pin for whatever problem that you know, you're working on, there's one you know, well-known strategy called the curriculum training. So to be fair, if the speed is too high, if beta is too large, to be fair, that's already, you know, pretty difficult problem to predict. And, you know, if you let the neural network to predict that from the get-go, it won't be able to, you know, make a good prediction. You know, since we're using, you know, the brain analogy, you know, neural networks are kind of like an intellectual creature, like a little child. Initially, it doesn't know anything about physics, and all of a sudden, you present a Einstein's, you know, general relativity to this little kid. I mean, there's a good chance that this kid will be lost, right? Understand nothing. You got to start from a simple, physics equation, maybe F equals to ma is a good starting point always, right? And then, from there you develop intuitions, and then you have to kind of, train students, step by step. You don't want to, you know, intimidate them with some really difficult example from the get-go, and then everybody will feel lost. So same thing, if we consider a neural network as kind of a student trying to learn something, you probably want to start with a simpler physics problem and let it learn to predict those simpler problems. And then gradually you increase the complexity of the problem. So that is the idea of curriculum training. So in practice, what this really means is, as we saw in the previous slide, when beta equals to 10, it does a fairly good job, right? So what you can do is to start with beta equals to 10 and pre-train the neural network with beta equals to 10. And then you increase beta by a little bit. So let's say instead of 10, now beta equals to 15. Generate the data, right? And then present beta equals to 15 to Pin, and then start from the previous, training session. You update the model, and in that way, you make Pin predict beta equals to 15. And then after that, you increase beta a little bit, make it 20, let's say, and then you fine tune the weights of the neural network with beta equals to 20. And then you basically repeat that process all the way up to beta equals to 30. And as a matter of fact, with that training strategy, the authors were able to train the same Pin model on beta equals to 30. Now we have, pretty good prediction result. And, quantitatively speaking, here's a table comparing the error, okay, the regular training of Pin on the left column, and then the curriculum training of Pin on the right column. And you can see that the error rate, there's a multiple orders of magnitude difference in terms of the error rate. So, almost all cases for the training of Pin, curriculum training is the must. So what that means is, you start from some simple, relatively simpler situation where, the fluid speed is, much slower. There's not a lot of action going on. You train the model and then, let the model converge first. And then from that, converged model configuration, now you increase the complexity of the physics problem, and then keep repeating the process is what you can do to improve the model. Does that make sense? All right, so here's another canonical benchmark, again from the same review paper. So now we consider 1D reaction diffusion equation. So reaction diffusion equation is an equation where, again, we have the physical quantity that evolves over time, and we have still 1D. So we have one-dimensional distribution of some physical quantity, and then that's evolving over time. And it's, it is some sort of a, equilibrium process, in the sense that, you start from some distribution, but then afterwards, it just set to, constant everywhere. Now, the diffusion term obviously, describes the diffusion phenomena. So the quantity kind of spread to the nearby region. But then the reaction term over here describes the creation of, of the material, and so on and so forth. Again, this one is slightly more complicated, equation compared to the previous one. And, for the exact solution over here, this is kind of the expected physical behavior of the system. But if you look at the Pin solution, we're kind of far from exact. And the reason why we're talking about this particular equation is because we have some sharp boundaries. So we have this, sharp, red color there. And then, this is kind of the, where the value U sort of drops dramatically, right? And then now we become to have a really low values in this region. So the ability to model that kind of sharp features is what we're testing over here. And unfortunately, Penn Solutions, for none of those cases, Penn was able to predict it properly. So for that, a very, typical, resolution of that problem is either of these two. One is what's called a sequence to sequence training. So instead of having the ambitious goal of predicting everything over the entire time, space time, all at once, you can divide the problem into smaller sequence of time. So you set some small delta t, and then using that small interval of time, you basically train Penn, and then make prediction over there, and then slide the time window to the next delta t, and then solve the problem on that next segment of delta t, and so on and so forth is one possibility that you can take. The other thing is the adaptive sampling, like what we've been talking. So those sharp features, obviously, if you have a uniform sampling of collocation points, you're going to lose those sharp features quite a bit versus when you do the sampling of the collocation point, you can have more collocation points near those sharp regimes, right? And in that way, you can improve the prediction accuracy of Penn. And oftentimes the adaptive sampling and the sequence to sequence training happens together. So you make a prediction of the first small delta t, and from that prediction you can have an idea of where the sharp features exist. So then when you do the next prediction for the next delta t, then you add more collocation points those near those sharp features, and then you basically repeat that process, and in that way you can have an adaptive samples of collocation point. And with those, obviously, you can have a better modeling accuracy. So this is kind of a very common, very well-known solution to some of the problems of Penn. One final thing I want to mention, I mean, you guys did a great job today because you already mentioned, a lot of potential issues of Penn, and you asked a lot of questions already. So I sort of explained that as I answer your questions. It's a good job. But just to kind of reiterate, optimization is a big challenge in Penn. So this is kind of a graphical visualization of the loss function, the mountain that we're climbing, or the reverse image of the mountain that we're climbing down. The moment we add physics laws, we start to have lots of wrinkles. Okay. And in terms of the gradient descent solver, if you have lots of wrinkles, it is inherently more difficult to optimize. So initially we had this nice sort of a plateau, and then in the middle there was a hole, right? So from the perspective of getting to the bottom of this hole, you start from somewhere, right, on this plateau, wander around following the gradient direction, and then the moment you get nearby the hole, you just converge to the the global optima. Versus now we have the physics laws, and then the physics laws terms add a lot of complexity to the terrain. So it's no longer the problem of just, wandering around this surface and then fall into this hole, but you have to kind of overcome all this, noisy local minima, right? And then if you're lucky, you'll discover this point over here, but most of the time, you're not going to be able to discover that very well. So sort of going back to the earlier question, what you want to do is to start the small, way like the physics laws, so that virtually we have a situation where we can ignore the physics laws, and you get to the hole as close as possible. And once you get close enough to the hole, you increase the importance of the physics laws, and then make it more rigorous, so that you can converge to a better solution. Is a possibility of what you can do. This, by the way, this beautiful visualization is done through a really nice mathematical method. And here, let me show you. A website called the lostlandscape.com. So this is not particularly, restricted to, physics informed loss terms, but this is a website where you can see lots of visually stunning, illustrations of how the loss functions of neural networks look like. Look at this. It's beautiful, visualization of the, loss function. And then you can see that there are lots of, spiky, local mins, right? So that's why, it's hard to train a neural network. So here, this is my favorite figure. What it does is to compare different hyperparameters and how the loss function landscape change as a function of hyperparameters. So under certain setting, you have a nice smooth, surface near the minima. But then for the settings that are not, so great, you get to see this noisy spikes, which is inherently harder to optimize. And there's a really nice paper associated with this website called the Visualizing the Loss Landscape of Neural Networks. Yeah, so if you're curious, I encourage you to take a look at the website, the lostlandscape.com, and then the paper associated with it. Seems like the internet today is a little slow, so maybe instead of waiting, I'm gonna move on. So this visualization is created based off of that loss landscape paper. So if you want to have a better understanding of what kind of problem they're solving, it like this is a one very good way of enhancing your understanding of the problem. Yeah. So here's another kind of perspective over here. We have the loss landscape for the same problem, and as one of you already asked, we have the coefficient over here. So when that coefficient is small enough, then we have relatively smoother surface. Versus when you have a larger coefficient, then you start to see lots of wrinkles, which makes it much harder to optimize. Yeah. So here's some comparison in terms of how we could. Sorry. Here's the comparison of the the error of training of the prediction for a 1D convection problem. And here, the lambda is the physical parameter. So obviously the physical parameter also determines the landscape of the loss function. And in a nutshell, as you can imagine, if the physical parameter goes into some, violent nonlinear regime, right? So in case of fluid dynamics, if you have a Reynolds number that goes beyond, maybe 1,000, 5,000, right? High Reynolds number regime, obviously the loss function landscape is going to go crazy and it becomes much harder to train. Or in case of, structural mechanics, if you have a stiffness, coefficients grow, then you have a really stiff system. And in those cases, again, you get to have an inherently difficult problem to solve. So again, the solution to that is the better choice of collocation points. So here we have another kind of sharp problem where, again, we have a 1D problem, and then it's evolving over time. And then this, evolving field kind of creates the huge contrast over here. So you could have the collocation point, redistributed like this so that we have more collocation points in the middle. And in that way, you could improve the prediction accuracy, but still, it's not terribly helping. So this is actually what I encourage you to do, with that PyTorch example. So in the example that we used, we had a relatively small angular frequency and then, a moderate amount of damping. And we were able to, make a pretty good prediction. But now we have, smaller damping and then a higher angular frequency. And as you can see, it struggles. And the number of iterations keep going. So it's not that, it has prematurely converged, but it is still kind of converging, but it doesn't seem to be able to find the global min, and the prediction result is way off, right? After a certain time t. Again, if you compare this with the landscape over here, it'll start to make sense. So if you have a more dynamic problem, the loss function landscape is going to be much more complicated, like on the right, and obviously training the model is going to be really complicated. So with that, I'm going to wrap up the physics and neural network lecture. After the break, we're going to come back to the PyTorch example. One thing that we haven't discussed yet is the data-driven discovery of the equation. So we're going to see that example using the harmonic oscillator. And then I'll show you the heat equation example, just so that you have some more sophisticated example to connect with your problem. So thank you all, and I'll see you in